Okay, welcome back. Now I come to a problem I'm calling acceleration of an incline and falling block. So we have here the wall, we have a hook connected to the wall, and then we have a string, we have a pulley here, okay, and then the string goes under the pulley, then goes over another pulley. This pulley is connected to a big incline, has a mass m, and this one here has a little m. There's a coefficient of kinetic friction here. Coefficient of kinetic friction is we can say certain value. Let's just give it a certain random value, k for now, right? And then we can say as this one is falling, what's going to be happening? How fast is it going to be accelerating? How fast is this going to be accelerating? For the big incline, big M, we're assuming there's no friction it has with the surface. So that one is frictionless. So what's going to happen? Well, we can argue that whatever acceleration this one has, as this one is falling, right? It has a certain acceleration, we can call that A1, right? Then when this one falls, right, this string is going to go up, and then this pulley is going to get closer to the wall, right? So that means this big block, big M, is going to be going to the right with the same acceleration that the falling mass is going down, right? So this one here is going this way, accelerating A1. And it is the same acceleration, right? In other words, this little m is also accelerating to the right with an acceleration a1, right? So it's not only going down with a1, but because it's connected to this system, this pulley is getting closer to the wall, right? That means the big incline also goes to the right with an acceleration a1. This one goes down with a1, and then it also goes to the right a1. So now let's do all the equations here, right? So let's, for the falling mass little m, what are the equations of motion? The incline pushes on it with a force of n, the normal force n, right? And then we have here the friction, its own weight, we have little mg. Then we have the friction force mu kn, right? So the normal force on it is going to equal little m times a1, right? Since it's accelerating to the right, with an acceleration a1, right? And then there is no other force in the x direction on the block, right? And then its weight has to beat the friction force because we know it's also accelerating down. So we can say here mg minus mu kn is equal to ma1. So this is little m, okay? Now let's do the forces on the incline, okay? On the incline, there's an action-reaction force, right? The incline pushes on the little block this way with a force of n, and therefore the little block pushes on this guy with a force of n this way, right? So on the incline we have a force like this, pushing it this way with a force of n. What other forces are there on the incline? If that was the only force on the incline, that means the incline should be accelerating to the left. But we know it's not going to accelerate to the left. The incline is also going to accelerate to the right. What's happening here? Well, actually, I forgot to draw the picture. The bottom pulley is connected to the incline, right? You have to have that connection. Otherwise, this pulley will fall, right? There's a connection between this pulley and the incline. So what's going to happen? Well, here, look at the intricacy of what is happening here. There's a tension T here in the string. And then there's a tension T pulling up on the pulley. Now, if we're assuming that the pulley is massless, it really doesn't matter the forces on the pulley itself. But this tension T is going to be the same tension because the pulley's mass is assumed to be negligible, right? So there's a pulley, the tension T pulling on the pulley this way. Then there's a tension T pulling on it this way, right? So this T and this T are the same because we're ignoring the mass of the pulley, right? And therefore, whatever tension T is here, the same tension is pulling the block this way, right? T. So that's the force that makes the incline accelerate to the right. You see, tension T. Okay? So the tension T in this string is equal to the tension T connecting the pulley to the incline. So this T and this T are equal. And then this T pulls on the incline this way. So we can say here, T minus n is equal to big M A1, right? Since we know that the incline is also accelerating to the right. Now let's follow the tension in the strings and let's follow what happens. There's a tension T here, then there's a tension T here, then there's a tension T pulling on the top incline this way, then there's a tension T this way, and then there's a tension T pulling it this way. All of these T's are the same, right? This T is the same, this T is the same, and then the tension T also pulls on the little block up. So that means there's another force on the little block. You have to have another force. Besides its weight, and besides the friction force pushing up on it, there's also tension T pushing on the block up, right? It's the continuation of this tension, 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 and all the way connected to this block, right? So the mg has to now not only beat the friction force, but it also has to beat the tension that is trying to make it accelerate up. So we have here mg minus mu kn, then we can say minus t is equal to little m a1, then n is equal to ma1, so these two are the forces on the little block, little m, and then these are the forces on the inclined plane, t minus n is equal to big M a1. So what do we want to solve? We want to solve for a1. What are our unknowns? Our unknowns are n, t, and a1. Okay? The one that I'm most interested in is the acceleration of the system, right? The acceleration of this block and the acceleration of this block and so on, right? So that's the one that we're interested in. So how can we combine these three equations? Okay, so how can I put all of these together? Well, if I add these two equations, this plus this, right? Then that eliminates the n, and then I have t is equal to, then I can just add the right side of the equation, m plus little m a, right? Then I can take that and factor it into the first equation, substitute it into the first equation. Then I have here mg minus mu kn minus t is equal to big M plus little m a is equal to little m a. Okay? Then what I can do is I can take this n and also substitute it into that n, right? The little ma. So then I can say mg minus mu k little m a, right? Minus big M plus little m a is equal to little m a. Okay, and then take all the a's to the right side, and we're pretty much almost done. So then this becomes mg a 2m, so the little m and the m combine, plus mu km plus big M. Okay? And to make it a little bit simpler, I can divide everything by little m. And then the little m cancels. Then I have here g is equal to a 2 plus mu k plus big M over little m. Okay? So what would happen if the friction coefficient was 0? If coefficient of friction was 0, then the acceleration would just be equal to g over 2 plus big M over little m. Okay? And then you could say, well, what would happen if the masses were the same? Little m equals big M, so then the acceleration will just be equal to g over 2 plus 1, right? So then it'd just be 9.8 over 3, and that'll be 3.267 meters per second squared. Okay, so what would happen if the masses were the same? The inclined plane would accelerate to the right with an acceleration 3.267 meters per second squared. The falling block would accelerate to the right with an acceleration of 3.267 meters per second squared, and it would accelerate down with the same acceleration. Okay? 3.267 meters per second squared. Okay, what happens as the incline gets heavier, right? As the big M gets heavier. What if big M over little m is 2? Okay, that means the incline is twice as heavy. So then you have here A is equal to G over 2 plus 2, G over 4. So then it's going to be 9.8 over 4, so 2.4 5 meters per second squared. So that means the acceleration becomes less, right? Big M over little m is half. What's going to happen? What if the inclined plane happens to be lighter than the object, right? So then that means the inclined plane is like this. The object is made out of steel or something, and maybe the inclined plane is made out of wood, right? So then it goes like this. Okay, so then what would that mean? Right, so if this weighs less, that means it takes less force to cause it to accelerate on this tension T, right? So if this is, of course, if this one is heavy, right, the tension in the string is gonna get larger. So when this one is heavy, the tension gets larger, and when the tension gets larger, this tension gets larger, and if this one is light, when this tension gets larger, it causes this to accelerate quicker, right? So when the ratio of the m over m becomes half, the acceleration gets quite a bit larger. So what's the answer going to be now? So then it's going to be A equals g over 2 plus half, so 9.8 over 2.5. So that's going to be almost 4 meters per second squared, right? Okay, well, what would happen when big M over little m is 0? What would happen? Well, it would be basically as if this one wasn't even here, right? Imagine it's almost like as if it's not there. So then if the friction coefficient we're assuming was also 0, if this one was 0, it would disappear, and then the acceleration would just be equal to g over 2, which is 9.8 over 2, 4.9 meters per second squared. It kind of makes sense that the falling object would fall at half the acceleration of gravity, right? 4.9 meters per second squared, because there's two sides of the string that are connected to it, okay? On the opposite end, if the mass m over the little m was infinity, if the inclined plane was a lot heavier, then the inclined plane would never move. It would just stand still, right? And if that means the object would never move either, right? Then, of course, if the friction coefficient is larger, then what is that going to do? That's just simply going to reduce the acceleration, right? So, therefore, the overall equation, we have here g divided by 2 plus mu k plus big M over m. If the coefficient of friction is larger than 0, that's going to reduce the acceleration because, of course, it's going to add friction to the system, and this one is not going to be able to fall as quicker. Now with this problem, you can see a good example where you have a falling block and you have an incline, you have an intricate system connecting the two, and you can find the combined acceleration of the system, and then find the limiting case where little m is equal to big M over little m is infinity, and then big M over little m is 0, and then see if the answers make sense or not. Okay? Thank you very much.